So, the CPU schedulers that we were talking about in the last class, so they have got they can be divided into at least two different classes. One is a short term scheduler or CPU scheduler, and another is long term scheduler or job scheduler, and also there is another scheduler which is known as mid term scheduler. So, basically, so if you look into this classification, then this schedulers, so these can I can divide into three classes: short term, mid term and long term. Now, if you remember that process flow diagram, process state transition diagram. So, we have said that so the processes when they are residing in the disk. So, this is the created state, now created to the new state, that is by this admitted. Now, from this new it was going to the ready. If we look back into this state transition diagram, for this from the new state, so it was coming to a ready state, and from the ready state it was going to the running state. Now, what happens is that there may be a say 10 different users in the system. Okay. So, this user 1 to user 10, there may be 10 different users in the system. So, they have created some processes. Now, when these processes are created, so we may be choosy about which processes do we select to be admitted into the system. Why do we do this? Because like in a computer system, so that we have, so there are two types of elements that we have in the computing system. One is the processor, so definitely which will be doing the jobs, and other is the IO devices. Now, so both of them are resources as far as the computer system is concerned. This processor as well as IO devices, both of them are resources. So, what we would like to have in the system is that both the processor and IO devices, they are utilized 100% times, or at least to a very high percentage of time. Now, depending upon the type of process that we have in the system, so one of them may be achievable whereas the other not. For example, if we look into the database type of operations, then the computation that is involved is very less. Maybe in a database operation, so we have got a query to identify the people whose salary is more than say rupees 30,000 per month. So, that way the as far as the operation is concerned, it has to do lot of disk access, and it has to see like if the salary is more than 30,000 or not. At the same time, it does not have lot of computation there. On the other hand, suppose we have got this satellite data, and from there we are trying to predict the weather for the coming days. So, that way there will be lot of computation. So, we have got only a few images from the satellite, but after that the computation that is involved is very high. So, these two types of applications, some of them are compute bound. For example, that weather forecasting, so that is a compute bound job, and we have got this database operations, so which are IO bound jobs. Now, if in my system all the jobs are say compute bound job, then what will happen is that this IO devices, they will remain idle. And on the other hand, if there are all the jobs are of type IO jobs, then the processor will be idle most of the time. So, we want to make a balance of these two. Now, how to make a balance? So, this is controlled actually at these points. The thing that I was talking about, maybe the type of jobs coming from user 1, so they are say compute bound jobs. Similarly, coming from user 5, so they are IO bound jobs. So, that way at any point of time I can take a decision, like I can look into the ready queue and try to see what are the different types of jobs that we have in my system, what is the current load onto the processor and the IO devices in terms of their utilization, waiting queue and all, and then I can take a decision whether I should admit the compute bound jobs or the IO bound jobs. So, that may be the policy. So, this is done by the long term scheduler. So, long term scheduler it tries to find out the characteristic of the jobs that are coming for the system from different users, and accordingly admit some of the jobs, whereas making others to wait for some time to be admitted. So, this is the long term scheduler. On the other hand, if I look into the this part of the scheduling, that is I have got a number of jobs waiting in the ready queue. So, in this ready queue I have got a number of jobs waiting. Now, from here I have to select some job that will be going to the running state. Now, how do we do this thing? So, for doing this again I have to I have to look into the priorities of these jobs and many other parameters. Now, whatever we do, but it has to be done very fast, because whatever time I am spending here, so that is basically an overhead for the system. And since maybe I may decide that any job that is going to the running state, so it will be executing for say 2 microsecond, and then the CPU will be given to the next job. So, every 2 microsecond I have to take a decision like which job will be going to the running state. So, that decision must be made very fast. So, it cannot be of the order of microseconds again. So, how do we do this thing? So, this particular scheduler that is running here, which is known as short term scheduler or CPU scheduler, that has to be very fast, whereas this long term scheduler that we are talking about. So, this long term scheduler, it may take slightly more time, but it should give me a good mix of job. On the other hand, the short term scheduler that we are talking about, so that should be very fast, and it may not be doing that much of selection between the jobs. So, we will see that the scheduling policies of this short term scheduler, so they are very simple, whereas this long term scheduler, they can do some statistical analysis of the jobs that are given by different users, and accordingly try to do something to maintain the balance between IO bound and CPU bound jobs. So, we will see that in more detail later. So, coming back to the point that we were discussing, so this scheduling queues. So, we have got the short term scheduler or CPU scheduler, it will select which process should be executed next and allocates the CPU. Sometimes the only scheduler in a system. So, many systems we do not have the long term scheduler also, because we do not have that much of load in the system. So, that much of variety of users are not there in the system. So, that way, for example, in a laboratory environment, maybe the jobs are submitted by students only, and all jobs are of similar type, maybe they are submitting some assignments and all. So, we do not have variation between the jobs. So, that way putting a long term scheduler there does not have any effect, excepting wasting some time in doing the scheduling. So, that way we may not have a long term scheduler available in the system at all. So, this short term scheduler may be the only scheduler. So, this is invoked very frequently in the range of milliseconds or microseconds, and naturally it must be very fast, okay, because that is an overhead that is coming. And this long term scheduler, so it will select which processes should be brought into the ready queue. So, it is invoked infrequently in terms of seconds and minutes, and that naturally it may be slow also. So, it controls the degree of multiprogramming. So, this term degree of multiprogramming, so this actually tells like we have got how many jobs in the system. So, how many jobs in the system. So, this is actually the degree of multiprogramming. So, you can also refine this question to a bit like how many instead of jobs. So, you may also ask for classification, that IO bound and CPU bound jobs, IO bound and CPU bound jobs. Now, if this degree of multiprogramming is low, that is we have got less number of jobs in the system, naturally the system does not have much thing to do. So, system will remain idle for most of the time. So, that way the system throughput will be low. Now, if you find the system throughput is low, so one possible reason is that degree of multiprogramming is low. So, you try to induct more processes into the system. Okay. So, more processes are put into the ready queue. So, that way degree of multiprogramming goes up, and the system is expected to be utilized more. But there are some situations that we will see later, where we will find that the degree of multiprogramming is very high, but system throughput is very low. So, that indicates some erroneous or difficult condition that has come in the system, some undesirable situation that has come in the system, and there we need to reduce the degree of multiprogramming. So, when the system throughput is pretty low, but degree of multiprogramming is high. So, that indicates some malfunctioning of the system. So, we need to reduce the degree of multiprogramming in that case. So, this is a two sided sword you can say. So, you can increase it or you have to decrease it at some time. So, processes can be described to be IO bound process or CPU bound process as we discussed. So, this IO bound process is they spends more time doing IO than computations. So, there will be the many short CPU bursts, and CPU bound processes they spend more time doing computation. So, very long CPU burst. So, we to understand like what is this CPU burst and IO this IO burst. So, it is like this. Suppose we are writing a program. So, any program that we write, so initially it will be doing some IO operation. For example, taking back that quadratic equation. So, initially that program should read the values of a, b and c. After that it will do some computation, then it will be it will be getting the roots and printing it. So, initially there is some IO, then there is some computation, and finally there is some IO. So, that is the structure of our example that we took, finding roots of a quadratic equation. So, in general I can say a program, so it will be doing IO for some time, then it will be doing CPU for operation the computation for some time, then it will again do IO for some time, then again it will do computation for some time. Okay. So, these individual durations of this IO and CPU that are coming, so they are called the burst. So, this is called a CPU burst. Similarly, this is another CPU burst. So, like that. So, if a job is IO bound job, then what will happen is that this IO bursts will be longer, but CPU bursts will be smaller. So, the very few CPU operation will be required, but most of the time it will be doing IO operation. On the other hand, if a process is compute bound, then this IO bursts will be small and compute CPU bursts will be large. So, if you whenever the CPU is given to the processor or to the process, when the CPU is given to the process, so if you start a timer to see how much CPU time it uses before going for the IO burst. So, that may be a measure of the CPU burst. So, for compute bound jobs, so you will find that these CPU bursts are large compared to IO bound jobs. So, as I said that a good job mix, it should have both CPU bound job and compute IO bound job in the system. So, this long term scheduler, so it will try to get good process mix. So, that is required. So, we will see how this is done by different schedulers and all. Now, in mobile systems, so there are concept of multitasking. So, some mobile systems for example, the early versions of iOS allow only one process to run and others are suspended. So, this is a very simple system and only one process will be running. So, multitasking is not there. Starting with iOS 4, it provides for a single foreground process controlled via user interface and multiple background processes in memory running, but not on the display and with limits. So, there may be one process which is the user has initiated. So, that is the foreground process, and there are a number of background processes that are there in memory, they are running, but with a lower priority. It limits limits include single short task and receiving notification of events, specific long running tasks like audio playback. So, this is the different types of limits that we have in this system. So, if you look into Android, so it runs foreground and background with fewer limits. So, background process uses a service to perform the tasks, and service can keep running even if background process is suspended, and service has no user interface, a small memory usage. So, that is the structure of this Android. So, again it has got the foreground and background jobs. So, again the foreground jobs will be always running and the background jobs are there, but depending upon it is conceptualized in terms of services. Now, the context switch that I was talking about. So, formally coming to the definition of it, when CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via a context switch. So, this is the definition of context switch. As I was telling that maybe previously process 1 was running. So, now we want to suspend process 1 and start process 2. Okay. So, we need to keep enough information of process 1 in the PCB, so that later on we can start process 1 restart process 1 from that point onwards. So, that has to be done. So, we have to save the state of the old process into the PCB, and later on when we want to restart, so we have to restore the context from the PCB to the for the process. So, this is the saved state of the new process has to be copied, and we must save the state of the old process. So, this is known as context switch. So, context of a process represented in the PCB. So, as I told previously that the process control block is the place where you should keep all these context related information. Context switching time is pure overhead, and system does no useful work while switching. So, naturally we have to minimize the context switching time. So, this is just the system is doing some copy and restore, that is not coming into the execution of the process. So, that is basically an overhead. So, more complex operating system and PCB, the longer will be the context switching time, because you need to save and restore more information. So, context switching time will go up. Then there are time dependent on hardware support. Some hardware provides multiple sets of registers per CPU. So, for example, if you look into say 8051 or say ARM processors etc., you will find that there are multiple CPU register sets. So, that if you want to go from one process to another process, maybe one process's context is stored in one set of CPU registers, another process is stored in another set of CPU registers. So, switching between them is nothing but switching between the register banks. So, that way the context switching becomes fast. So, many of the processors that are designed now, they provide facility for in the hardware for doing this context switching fast, and that way it makes the whole operation, whole context switching to be done quite fast. And this is a very important issue that is that has to be taken care of by the architecture designers and OS designers. Next, coming to the operations on processes. So, system must provide mechanism for process creation, process termination, and similarly many other things that we will see slowly. So, process creation means I should be able to create a new process where I will try to do something new, and then a process has to be terminated. So, maybe it is voluntary termination or involuntary termination. So, voluntary termination is process ends telling that okay, I am over, and sometimes the processes they misbehave and the system administrator has to intervene and terminate the process. So, this process termination has to be there. So, both of them are required. Now, how do we create a process? Now, one process may create other processes, and there is a parent child relationship between the processes. So, parent process creates children processes, and which in turn create other processes, forming a tree of the process. Like, so, this is the init whose PID is equal to 1, and then this for example, in an Unix operating system, this init is the first process that is created, its PID is equal to 1. Now, this init process, it can create a number of processes, children processes. One of them may be a login process that prompts the user to enter the login data. Then there may be another process that takes care of the Python programs, the Python scripts. Then there may be a shell script SSHD, so that is there. Similarly, from login it can create another process called B shell or bash. Similarly, in the shell the user might have given some command to know the process status, or this some editor. Okay. So, this is some VI editor. So, this way we can have a number of children created from a parent process. So, generally a process is identified and managed via a process identifier. So, every process that is created, so it has got an identifier, and this identifier value, since one is reserved for init process. So, it starts from 2 onwards and it goes on incrementing one by one as newer and newer processes are created, and when it comes to some maximum value, then it actually rolls back to the value 2. So, expecting that by that time that process will be over. Of course, it should do a check that the PID is not duplicated. So, this is a typical tree that we have for processes in Unix operating system. Now, resource sharing among parents and children, the options may be like this, that parent and children share all resources, children share a subset of parents resources, and parent and child share no resources. So, these are the three alternatives, like maybe the parent has got some variables, some memory locations that are associated with the parent. Now, whether those variable locations will be visible to the child process or not, so that is one type of decision. In some cases, so we may want that those locations be visible. For some other cases, we may say that no, they should not be visible to the children processes. So, this way there can be different types of decision, and as so to be said frankly, so there is no hard and fast rule like which one to be followed, and different OS designers they follow different degree of sharing. So, all of these are common, like we can have this parent and children that share all resources, they may child may share a subset of parents resources, or they share no resources. So, that is a resource sharing option. Another option is that execution option. So, execution option may be that parent and children execute concurrently, and parent or the parent waits until children terminate. So, this is like this, that we have got a parent process. Okay, so, it was executing. So, when it came to say this point, so it create a new process. It has created child process. Now, what happens in the after that, again it goes on doing something else. So, it is like this, that this process, suppose this parent process was P1, parent is P1, and the child that is created is the process C1. Now, in my system I have got two processes, one is P1 which after creating the child will continue, and another is the new child process that is created. So, it will do something. Now, as far as this system is concerned, so there may be different options, like this P1 process, it may continue parallelly with C1, like in the ready queue that I have, I may have the entry for P1 as well as the entry for C1, and whichever process is scheduled by the short term scheduler, so that will get chance for execution. So, P1 or C1 may execute, and then that again that execution may be mixed up also, maybe C1 gets the chance for execution, C1 executes for some time and then it gets descheduled, and then this P1 gets chance for execution. So, and this range P1 executes, then P1 gets descheduled, again C1 executes for some time. So, it can happen like this. So, as if so P1 and C1 they are two parallel processes now. So, there is no dependency between them. So, they are two parallel processes. Other possibility is that once this P1 has created the child, it waits for this child to be over. So, this is waiting. So, as soon as this process is created, child process is created, the parent process P1 it is put into some event wait state, it is put into some event wait state for the child to be over, and only when the child gets over, then the process P1 will be taken back from that wait state and will be put back onto the ready state. So, that way it will wait for some more some time when the child process is executing. So, parent is suspended. So, again these are the two different thoughts. Okay. So, it is not mandatory that one of them will always be superior to the other, but both of them are available in different operating systems, and many operating systems, so they will provide some mechanism how you can make the parent process to wait for the child, and sometimes we want that, sometimes we do not want that. So, accordingly we have to use the facilities provided by the operating system. Now, regarding the address space, so this address space, a child is a duplicate of the parent address space. So, this is one option. Other option is that the child loads a program into the address space. So, like the parent process, so it had its code data and stack segments. Now, it may so happen that the child process it also uses the same code data stack segments of the parent process. So, this is one possibility. Other possibility is that since this child is a new process, it should have its own code data and stack segments. So, that is the address space of the child is totally different from the address space of the parent, and we can have this address spaces loaded separately. So, if you look into this Unix operating system, So, it follows a mix up of all these things, like it for creating a new process. So, fork is the system call. So, this fork system call, it creates new process, and then there is a exec system call that can be used after a fork, that replaces the process memory space with a new program. So, by default when the so if you look into the parent process, so parent has got this code, data and stack, this code segment, data segment and stack segment. So, this is the parent process. Now, when the child process is created, so it uses the same code segment, the code part is shared. So, this is shared, but this data and stack, so they are separate. So, they are new, but it is copied here. So, this is also copied here. So, this is a copy, this is a copy, and this is same, that is shared. So, code part is shared, but data and stack are separate. So, if I write a program like this, say I write a fork here, and after that I write a print hello. Now, if this program is executed, then after this fork has been done, so I have got two processes, the parent was there and a new process child is also created. Now, since the parent will continue, so parent will print this hello to the screen, and since child is also using the same address space as the parent, so child will also execute the code and it will also print the hello. As a result, this hello will be printed twice. Okay. So, this code part is shared. Now, the data, so if I have got a variable x here, so if I have got an integer x in this in the data segment, now it will also have an x here, but this x and this x, they are different. For example, going back to the previous case, like if I say that if this is the parent process and here it assigns x equal to 5, then this x equal to 5 will not be visible to the child process. So, so for example, if this parent does, after forking it does x equal to 5, so that is not visible to the child process, it will see the old value of x. So, we will see that in more detail, but another thing is that so this is by default what is provided by the Unix, but we may not want it. So, we may want that the child should do something new, and for that purpose there is another system called exec. So, what this exec call does is that it replaces the process's memory space with a new program. Maybe the new process that I have created, here I want to execute some other program. So, what it will do, this exec call, so it will overwrite all this portion and it will be loading, it will be copied with the new program that we want to execute. So, that is why this child process will be executing a new program. Now, the parent process may wait for the child to be over. Okay. So, when the child process executes this exit on completion, then it sends an information to the parent process which was waiting, and this wait process, this parent can continue from this point. So, these are the different system calls that we have got. This fork is one system call for creating, exec is for overwriting the memory part for the new for the child process, and exit is for exiting the execution, and the exit will give information. If the parent was waiting, then it will get the information that the child is over, and it can, if it wants that type of synchronization, then it can resume from that. Ideally, if this exit is not there, then this parent will not, and parent has not given the call to wait, then this, after this point, this parent and child, they are two parallel processes and they are scheduled independently. So, that way it can continue, but if this wait is there, then there may be synchronization between parent and child. So, parent will wait for the child to be over and then only it will continue.